A satellite S is moving in an elliptical orbit around the Earth. The mass of the satellite is very small compared to the mass of the Earth. Okay, so over here the acceleration of S, so we have to find out the various things: the acceleration, the angular momentum, the total mechanical energy, okay, and everything. Okay, now first of all, let me draw a little bit of 3D diagram. Let us say this is moving in an elliptical orbit, in any elliptical orbit around the Earth. Okay, suppose this is the Earth, okay, over here, and the satellite is moving in an elliptical orbit around the Earth. Its acceleration will always be directed towards the center. Okay, the acceleration will always be directed towards the center. So mv square by r will be equal to, over here, mv square by r for moment. Okay, for a moment it will be equal to gmm by r square. So the acceleration will always be directed towards the center of the Earth. So option number A is correct. We have to find out the angular momentum. Okay, angular momentum is given now by Kepler's law. The angular momentum remains same in equal in magnitude as well as in direction. Okay, how will I get the value of angular momentum? Over here I can say that L vector will be equal to, okay, it will follow the same law as that of, okay, v vector cross r vector, or r vector cross v vector basically. Okay, so r vector cross v vector over here. So over here I can say that okay, it will be equal to, if I draw the v vector, the velocity vector remains somewhere over here and the r vector is towards this part. Okay, so r vector cross v vector will always be perpendicular to the plane of rotation. Okay, and the direction as well as the magnitude remains same. So option number B is also correct. Okay, so option number B is incorrect. Okay, because it is given that the angular momentum is about the center of the Earth changes in direction. No, in direction also it remains same, and in magnitude also it remains same. The total mechanical energy of S varies periodically with respect to time. Okay, now in order to calculate the mechanical energy, we have to find out the formula. Okay, that is, over here I can say that the total mechanical energy will be equal to kinetic energy plus the potential energy of the rotation. Now let us assume that the mass of the satellite M is very small as compared to capital M. Okay, so forget about the rotation of the Earth, let us concentrate only on the rotation of the mass. Okay, the kinetic energy as well as the potential energy will remain same if there is no friction. Okay, since there is no friction in space, I can neglect the whatever is the due to debris and everything, I can neglect that part. So I can say that there is no friction in space, so the sum of the kinetic and the potential energy will remain same. Okay, individually they will change, but the sum will remain same. Okay, as the satellite approaches the planet, the kinetic energy increases, okay, and the potential energy over here decreases. Okay, when I consider the sign, over here, the potential energy will decrease and the kinetic energy will increase. Okay, so over here, but the total energy still remains same. Okay, the total energy will remain same. Okay, so option number C is also incorrect. Option number D, the linear momentum of S remains constant in magnitude. Linear momentum will be equal to m into v. Okay, m into v vector. Okay, forget about the vector sign. They have asked only the magnitude. Okay, in an ellipse, when a satellite or any object, okay, approaches the planet, the velocity increases as it moves away from the planet. Over here the velocity decreases. Okay, the velocity decreases over here. Okay, so over here the velocity does not remain same, so the linear momentum will also not remain same. So option number D is also incorrect. Okay, so the correct answer is only option number A.